Okay, I think we can start. Yeah. It's a pleasure to welcome Christian Hammer. Christian Hammer is a postdoc at Purdue in the computer science department. His PhD work was on information flow analysis for Java, and he has done program analysis research mostly for Java in the past. Today he will be presenting current research done here on security of JavaScript.
Thank you, Jan. So welcome to my talk today. I'm gonna be speaking about security of JavaScript in a browser environment. And so the question is, why would that matter at all? So today we have the Web 2.0 that is much more interactive than we used to have it in the beginning of the internet. We have much more scripts that are going on when you load a page. Besides, pages today are not just from a single source usually, but you load scripts and other content from different sources. So you don't know what the page will look like in the end up front. For example, you might have ads that are integrated into the main page from an unknown script, so you might or might not trust it. Other content that you might have is user-created programs. For example, in Facebook, users can create apps. And all that gives the opportunity kind of to inject scripts into your browser, which allows cross-site scripting and CSRF attacks. I will talk about these in a minute. So what is even worse about JavaScript is that it is a very dynamic scripting language. It can pretty much change everything at all times. It's executed at the client, so it's executed in your browser of the user, and it has access to all the data that's stored in the client. For example, it can send data from your browser to some server outside, which raises questions about confidentiality. And it can also change all the data at your client, which raises questions about integrity. So everything can happen here, and it's not sure what will happen. For example, we have seen attacks coming from advertisers in the past, one of which was scareware that was showing at the New York Times in 2009. First, this advertiser was posing as a legitimate advertiser, but suddenly they switched to showing a fake virus warnings and making people buy their fake virus scanner. Another example is that in German newspapers, people were having malware because of an advertiser. So what they did, they scanned all the plugins that you have in your browser and were looking for vulnerabilities, and if they found them, they injected some exploit. So all these show that with JavaScript and untrusted code, you have a big security risk in your browser. So what is JavaScript offering in your browser as a remedy? Traditionally, you don't have a very big set of tools. Most importantly, you have sandboxing in your browser. So JavaScript has no file system access whatsoever, and it cannot do direct system calls. Then, besides, there's only like smaller issues. For example, you cannot create windows that are very small to make sure that people see what is actually on the screen. And sometimes browser history is not visible to JavaScript, or you cannot unconditionally close windows. Excuse me. But these are kind of dependent on your browser, and it's not a lot of security that's offering here. The most important security mechanism in your browser is the same origin policy. It guarantees isolation of documents, and it says that only the site that stores some information in your browser may later read or modify that information. So for example, if you have two tabs open, one of which is your bank account and the other is something else where you're browsing in the internet, you would not want that the other tab can read something from your banking account, right? You would not want that. And this is prevented by the same origin policy. So it actually guarantees that if you don't have the same protocol, host, and port, then you will not be allowed to read from the other document. There's one minor exception here. You're permitted to set your own domain to a suffix of the current domain, which makes sure that you can go to a mother page, right? The same origin policy is also very important for cookies. Cookies are partitioned according to a page origin, and they can only be read and written by the same origin. However, if you have frames or inline frames, then these might have a different origin, what is shown in the frame. And so the browsers may still be able to access data from a third party. And so many browsers offer a third-party cookie blocking facility because of that. And as a last issue, what I wanted to show you is the top 10 of the website problems out there. There's an organization that's called OWASP that is looking for vulnerabilities in browsers and web-based applications. And that top 10 security list is started with code injection. So what we have here is that untrusted data is sent to an interpreter and is part of a command. So data becomes actually code, which is not supposed to happen, right? So what happens here is that someone injects data and tricks the interpreter into executing this command. This allows modification, altering, or deletion of sensitive data. And examples here are SQL, operating systems, and LDAP. But the same issue is also possible with JavaScript, and this is just a different topic here, but it's actually pretty much the same. It's called cross-site scripting, and this happens when you have untrusted data that is sent to a web browser without proper validation and escaping. So your browser, or the browser of the victim, will execute the script even though it's supposed to be only data. And with that, you can hijack a user session, deface websites, redirect the user to a malicious site, and so on. So how does this work? An attacker sends a simple text-based attack and exploits the syntax of the JavaScript interpreter. This text, the JavaScript text, can come from almost any source, including some internal sources. And the injection flow will only show up when the data is sent to your browser. As an example, I have here a small script. Unfortunately, I cannot use the mouse here. So if you have a script that changes the document location to some site that the attacker controls, they can insert the document cookie and steal your credentials of the site that you're currently browsing when you're logged in, obviously, right? And as I said, a script may come from all kinds of data. For example, it can come from form data that the user enters. It can come from unprotected file system resources. It can even come from a database where you stored it previously, or from a cookie value. The fact that cookie value is stored in your browser does not prevent that the user that's sitting in front of the machine is not able to change it. So cookies are not to be trusted. Another topic in the top 10 of security risks out there is cross-site request forgery, called CSRF. And here it's very similar. You have some code injection. And this code injection sends a forged HTTP request from a logged-in victim's browser. And browsers, when you're logged in, they will also send the victim's session cookie and other credentials along with the HTTP request. So for the web application, this sounds as if these are legitimate requests. They cannot differentiate. So how does this happen? An attacker creates a forged HTTP request. This is, as I said, automatically using the user's credentials if you're authenticated. And you can use cross-site scripting or other techniques to send the request. And usually it's very easy to predict the details of a transaction because they are usually always the same. They just take some parameters and you have to fill them in. So if you're able to inject the script, you're pretty much able to do everything that a logged-in user is able to do. Other attacks you can do with JavaScript is to include code from a trusted source, supposedly trusted source, I would say. Like we have seen, ads are not always trustworthy. But there's also other issues here. For example, there's apps in your operating system for the widgets or other programs that use JavaScript, and they are executed in the browser or at least in the browser session. So they could do pretty much the same as I have been describing before. And the browser offers no sandboxing of the original hosting code against the third-party code. So they actually happen in the same global namespace, and everything is accessible and alterable by the external code. And I have a short demo that illustrates that. So here we have a typical login window where you're supposed to use username and password. And this is a page that's composed of the host and an advertiser. You cannot see an advertisement here, but there's another advertiser here available. So if I just type in something and log in, I would assume that this goes to my site because this is where I'm logging in. But unfortunately, this is going to a different server which has been changed by the JavaScript advertisement. So they changed the server that is the data is being sent to this evilxy.com. That's what the advertisement did. This is like a 10-line of code JavaScript example. And another idea here would be to see some credentials. And what you could do here is you type something in, and even before you send it out, the advertisement can actually read everything that's in the document, and you can see down here that this is exactly the thing that I already typed in. So even before sending it out, an advertisement can read everything that's in a document. Oh, there's a question here?
Yeah, I have a question that refers to that.
Oh, yes. Mm-hmm.
You said so the JavaScript changed the host that the use of their credentials being sent to?
Right.
So did they have to bypass some margin policy to do that for that attack?
No, because they are ending up in the same document. That's what I said. They happen in the same namespace. There's no sandbox or whatsoever in between. Because, so what happens here is that the host actually loads a script from a foreign server.
So it's lining into the ad servers.
Right. It loads a script from the ad server. And so there's no difference for the browser. Right? Okay.
So are we assuming that the ad server here is malicious?
So the ad server here is malicious, obviously, right. Mm-hmm. Okay. So let's go back to the presentation. Okay. So we've seen what can happen in your browser. What could you do to prevent these malicious attacks, right? One solution would be to escape all untrusted input. So for example, if someone inserts a script tag you would change the script tag and insert greater and smaller signs instead of the tag angles. But this is not always what you want. Sometimes users are supposed to have scripts in the JavaScript, right? So when you load an app, the advertiser usually installs the advertisement with JavaScript. So you need to allow them to do something. You cannot always exclude everything. So another idea people had was rewriting techniques. For example, Facebook JavaScript is a dialect that does rewriting, but also the Yahoo AdSafe and Google Caja do similar ideas. They rewrite the JavaScript that you are loading into your page. However, this is prone to obfuscation because first, browser parsers are not the same in all browsers. So some browsers might accept some JavaScript that others don't. And browsers are very lenient. I have examples for that coming up in a few minutes. And because of this filtering, there has been a lot of exploits already. So for MySpace, a very popular thing in the beginning was adding someone called Samy. But this was not because Samy was really popular, but because it was a worm. And I will show the code in a minute for that. For Yahoo Mail, there was a virus called Yammer, and here the filter actually introduced a malicious script. So what happened here was that you had a target tag, but a target tag is not allowed in Yahoo Mail. So it was filtered out, and because of that, the unload tag actually became active for the browser. So filtering might be a solution sometimes, but it can also be a problem. And for Facebook JavaScript, there has been people around that found several problematic issues too. And so there's more to come. It's not guaranteed that filtering will solve all these problems. So let's have a look at the Samy worm. How did that work? So MySpace blocks most tags. In particular, it blocks script tags, JavaScript. But some browsers accept JavaScript even in a style definition. So here the background style was defined as some JavaScript. So this did not work in all the browsers, but if you want to spread a worm, it's enough if enough people have such a browser, right? But since we can see that the single and double quotes were already used here, they could not use a different, more layers of quotes. So they had to find some possibility to use more quotes, and one thing they could do was to define an expression in HTML, like the one here. The expression is alert ha, and then the JavaScript can access the HTML, and so now they have a third layer of quotes, right? But then again, MySpace stripped out a lot of keywords that you would use for a worm. For example, the word JavaScript was filtered out. But browsers are, as I said, very lenient. So, for example, if you write Java, new line, script, most browsers will parse this as the keyword JavaScript, which is not what you would expect, but this happens. And the MySpace developers did not expect that either, so it was not filtered. Other document tags that were filtered was, for example, inner HTML, which is used to access the HTML source of a document. And here they used a different trick. They split up the word inner HTML into two strings, and then MySpace was no longer able to filter it. As you can see here, they were using ini plus r HTML, this is not filtered anymore. So static filtering is really not very powerful, right? The same idea was used for a function that they wanted to use for AJAX calls. And so now they can set the document location with JavaScript that they need for a certain domain. They can do AJAX calls to have post and get calls. And finally, with these techniques, they were able to add the user Samy as a friend, because this allows everything you need to do for a CSRF attack. Okay. So besides what is out there for your everyday life, what does science offer as a remedy? Most solutions that I have found in literature are actually based on filtering as well. So they have the same problems. We have seen that using a parser's browser introduces dependence on that browser and also on a certain version maybe. If you use an independent parser, you will miss something because you will never have the same parsing. And there's one more issue here. In JavaScript, you can create another script at runtime. You can use something like document write, and with document write, you can write another script into your document at runtime in your browser. And static filtering techniques have a hard time with that. So what would be good design principles for security? What one would like to have is complete interposition. All the scripts that are run in my browsers have to be protected by the security mechanism. So even if I have scripts that are created by scripts, they should be monitored. That should be clear. But one would also want to have tamper-proofness. So user-created scripts must not be able to circumvent the security mechanism or tamper with it in unintended ways. So for example, if you define the security mechanisms in JavaScript, then the user script should not be able to change that policy. Which makes sense, right? And if you have those two design principles, then you have soundness for your approach. But there's more. Besides that, what you would want to have is transparency. So if your web page already adhered to all your security policies, then its behavior should not change. Only if something that you did not want to have according to your security policy, then the behavior should change, right? And the last thing is flexibility, which means the separation of the security mechanisms and the security policies. So if you change the security policies, you should not have to change the security mechanism. So now I will present some papers and works that have been proposed in the past. One is called BrowserShield. And BrowserShield rewrites the pages along with all the scripts that are included into safe counterparts. It inserts runtime checks even if you have dynamically created scripts. And this was proposed to prevent known vulnerabilities in Internet Explorer, because people, especially at universities and companies, they usually do not patch all the browsers immediately, but they first have to check that no side effects will happen when they do the patching. So it sometimes can take weeks or months until they will actually apply the patch. And to close the gap between the release of the patch and the installation at a client, they were proposing to have a security policy that prevents the exploit of that vulnerability that they were closing with such JavaScript. However, this was only able to parse 70 out of 250 samples correctly. So we can see that creating a good parser for JavaScript is not very easy, right? So another approach that I have seen is called lightweight self-protecting JavaScript. They are using ideas from aspect-oriented programming, and this circumvents parser mismatches because you're interposing some functions of your browser in JavaScript. So what they do is they wrap some native functions and only execute the original if some policy is abided. And here they have to make sure that only the wrapping function will reference to the original function. Otherwise, you could come back to the original JavaScript function. However, it's not clear because you could use iframes, and these iframes might have access to the original function again. Or in some browsers, if you delete the function and it's a native function, the original function will be restored. So you can circumvent this policy, right? So let's show a quick example how this would work. For example, if you have window.eval, which allows dynamic code execution, you would want to define a safe version of that in the end calls the original function. However, there might be several aliases to the same function. For example, window.eval and window.parent.eval would point to the same function. And there may be more. Maybe some of them might be browser specific. So it's kind of hard to guarantee complete interposition here, right? And some native functions cannot be redefined. For example, in Internet Explorer, the alert function that shows a pop-up cannot be redefined. Another idea that was presented in literature is called detecting malicious JavaScript code in Mozilla. And they are directly introducing their monitor facility into the browser, and the output goes directly to disk. And so now you can check what has been written to disk and compare it to a high-level security policy. But since this is only possible after you check what has been written to a file, this is only post-mortem analysis. So if something bad happened, you cannot prevent it. You can only find out later on. And another idea that came out is called browser-enforced embedded policies. And here the policies are embedded in a web page as JavaScript. And they propose white and blacklisting. So they assume that the web page designer has perfect knowledge about all the allowed scripts for whitelisting. But this is usually not the case. If you, for example, want to load an advertisement, you will not be able to know the script that's executed by the ad. The alternative would be blacklisting, which is called DOM sandboxing in their approach. So they could mark a certain div tag in HTML as untrusted, and this would not allow to do any JavaScript in the subtree of the document tree. But then again, advertisements are usually installed with JavaScript. So not allowing any JavaScript does not solve advertisement either. So this works only for very restricted HTML and JavaScript applications. Gatekeeper is a new approach from Microsoft. They did mostly static analysis for two subsets of JavaScript. One is called JavaScript Safe, which is statically analyzable. For example, they have no dynamic code execution, no evaluation of strings. But to be able to analyze more realistic scripts, they had to allow some some constructs that are dynamic and are essentials for the operating system widgets that they have been checking. And I just did that based on the usage. So the most common constructs were added, other constructs were not added. So they found that 22% of all the samples that they had were neither in JavaScript Save nor in JavaScript GK, and they had to be rejected. So the other, about 80%, could be analyzed. That's at least something. But the code base they used, because of the widgets, are very small, so it was around like 200 lines of code. But for a smaller JavaScript applications, you can even do static analysis, even if the language is very, very dynamic. And another static analysis that has been proposed is called staged information flow for JavaScript. Here you already analyze the known code, because that's your own code that's known from the server, and it can be analyzed before being sent to the browser. But then you have to check a residual policy that comes from integrating foreign scripts in the browser of the client. Here they are assuming that if you create field names dynamically, which is possible in JavaScript, so you could have something like adding 2 strings and then use this as a field name, then they do not coincident with statically known field names. So it's kind of easy to circumvent such a technique if you know that a website is using this. And they do not also support full JavaScript. They have some constructs that they cannot handle. But again, parts of JavaScript can be statically analyzed. And the newest approach that I have found is called ConScript, and it will be presented at Security and Privacy this year. It's coming from Berkeley and Microsoft Research again, Meyerowitz and Lifshitz. And this is again integrated into the browser, into Internet Explorer 8. And you can express some fine-grained application-specific security policies, and these are enforced at runtime. So they show 17 examples of policies. They even propose that you can automatically generate policies, which sounds very nice. And they have an information flow control type system that ensures that your policies are sound. So how does this work? They have something that's called deep advice. So the idea is similar to what we had in a different paper that I have presented before. But instead of rewriting something in the browser, in JavaScript, they interpose their policies directly in the browser. So this guarantees complete interposition. So if you say this function should be monitored, then the browser guarantees that no one can access the function without actually having the policy being run before. Again, they propose mostly like white and blacklisting approaches for critical functions in JavaScript and also for script introduction. And this allows to formulate some more complex policies, like you cannot create a link after reading the cookie, because that link could include your credentials. Right? If you read the cookie, you know the credentials and you can send them out. So how do they secure that advice? They have found out that policies are very tricky to get right, even if it's only like a few lines of JavaScript. And so they split up the code into kernel code that's coming from the host and the user code that is untrusted. And to protect against advice tampering, they modify the interpreter to enable isolated reasoning. And I've got an example here. So the first line shows a whitelist. For example, everything that comes from Google is supposed to be trusted. And then the around keyword installs an advice. So it says, when calling window.postMessage, do the function that's behind here as a parameter. And so this does check if the target is in OK origin. And if it's not, then it will throw an error. Otherwise, it will go back and call the original function, which is the first parameter, with the message and the target it was intended to get. Is the syntax here clear? No questions? Okay. So what could happen in JavaScript here? Someone could redefine the toString method, for example. So what an attacker could do is, the first time toString is called, they could return google.com. So when it is checked, if something is in OK origin, then this will be OK. But when it is actually called in the last line of the policy, then they will return evil.com. So you can see this is kind of tricky, right? So only the first time when the policy is checked, you are returning the right thing, and when it's actually executed, it's returning something else. Another attack vector that could be done here is function prototype poisoning. So what you could say is that each time you do a call to a function, you should do window.postMessage to evil.com. And so now if you call postMessage, what would happen is it is checked. And because you entered google.com, this will be detected as OK. But when the last call in the last function, in the last line of the policy is done, this will call the function from the function prototype. And so it will not call the original function, but it will call window.postMessage for evil.com instead. So as I said, JavaScript is a very, very dynamic language. You can pretty much change everything here, right? And this is one of the examples. You can even change what will be called at runtime. Another option that attack vector could be, you could change the prototype of object, which is the top of the type hierarchy. So you could install the string evil.com and say that this would match to true. And so now if you call postMessage with evil.com, it will not be found in OK origin. But then the finding mechanism will go up and go to the object prototype, so which is kind of the superclass, and it will check over there. And there it finds that evil.com is matching to true. So OK origin of target will return true. So again, this is a very, very dynamic construct. And this is not what the people probably writing the security policy had in mind. Another thing that could be done is changing the way that a get function of a property would work. This is not possible in all browsers, but it is possible in the most widespread browsers. You can even change how something works when a property is read. So for example, if you want to read the property evil.com, then this could delete google.com from OK origin. So this is a combination with attack 3. You can even edit the whitelist. So again, a very, very dynamic language, and it allows a lot of attacks. So what would be a safe policy for ConScript? In their paper, they define some new constructs. And for example, the to primitive makes sure that you first convert the target to a primitive, for example, to a string. And so you would not allow the first attack vector because it is only calling toString once. And then it will check with a hasprop. This will check only in the original object and will not go up to the prototype. So you cannot do prototype poisoning here. And then they have something that's called ucall, which will only do a call to the original object and also not go up to the prototype. And this will prevent all these attacks that I have shown you before. But they had to change the language for that, right? And with these constructs, they are very static. They can do static typing, and they have an information flow control type system that shows if a policy is safe or not. And this policy is safe. So what would be the shortcomings of this new approach? Well, whitelisting and blacklisting are mainly best practices. So you can prevent some problematic constructs, but you can only prevent something based on previous attack vectors. It's not a semantic criterion, right? So it's like virus scanning. If you have not seen a virus before, you will not find it. So it more cures the symptoms than the disease. And one other issue they have is they do not yet have some option to instrument a function that's created by a library call without trusting the library. Because when you load the library, you don't know yet what the function will be. And in order to instrument it, you have to know the function. So this is still unsolved, but maybe then they can come up with something in the future. So what we have been thinking about is a new approach that's based on JavaScript sandboxing techniques. So what we would like to do is something like executing untrusted JavaScript in a monitored environment. And if we do not see a security violation, then the effects become visible. Otherwise, we want to prevent them or terminate the script altogether. And how to implement that? We would instrument the open source WebKit JavaScript engine that's used, for example, in the Safari web browser and in other open source web browsers. So when we detect an external script, the monitoring is enabled, and the interpreter intercepts events, and finally it will check whether malicious behavior has been found or not. And then we could prevent the violations or stop the script altogether. So right now, we do not plan to have a complete information flow control mechanism, but more a conservative approximation. But this could be extended to a complete information flow control mechanism. In our group, we have previously analyzed the dynamics of JavaScript, of realistic websites out in the wild. They had analyzed the top 100 sites that were coming up. So we know how JavaScript behaves in practice. And we have also analyzed the interactions between components of mashup pages. So we have found that sometimes the host page will create data that is actually used by an advertisement. So sometimes the advertisement should be allowed to read or modify something that's coming from the host. That's intentional. So we would need to have a specification mechanism for allowed information flow. Okay, this lets me come to my end. I have presented today security mechanisms for JavaScript. I have shown that security for JavaScript is an issue in the wild and that filtering does not solve the problem. Currently, there is no silver bullet to JavaScript security. But we have seen that with good software engineering standards, you can prevent cross-site scripting and CSRF attacks. But most current applications propose browser-integrated sandboxing for external code. And this seems to be a promising approach for the future. Thank you very much. Any questions? Yes.
Can you tell us how, or any possible ways by which we can prevent double URL encoding cross-site scriptings, basically?
Can you please repeat? I didn't understand the question.
Can you explain any ways by which we can, or do you know of any methods by which we can filter cross-site scripting which involves URL encoding, especially double URL encoding, wherein you encode already URL encoded input once more, so that some web servers don't detect it, so it escapes sanitization, basically.
Right. So as I said, there's all kinds of obfuscation methods for cross-site scriptings, and this is probably one of them. So you can encode HTML in various encodings, and currently I'm not sure if there's techniques out there that detect these encodings. I'm not aware of that. Maybe there is. I don't know. More questions? Okay, then thank you again for coming.